Okay, so it looks like there is a couple people from Twitter. Hi, Brendan. Are you giving the talk at Talk Math with your friends? That's me. Oh, awesome. We're going to advertise your talk uh, after our talk today because it's very much a great follow up to this one, and I look forward to being there at your talk tomorrow. I see there's a couple other people coming in from Twitter. I'm glad that we advertised by Twitter. Is there anyone here from research seminars who saw this on researchseminars.org? Hi, Tom. Good to see you.
Good to see you too.
Tom Edgar is the editor of Math Horizons. I think I probably have a copy right in reach. Absolutely wonderful fellow. Our paper with Brian, the speaker today, appeared in this issue. Wonderful reading.
And it's a great magic trick. It's a great magic trick.
Yeah, I don't think Brian's going to talk about mathematical magic today, but he'll enchant us somehow. Brian, are you with us?
Hello. Yeah, I can hear you.
Hello, great. Do you have slides to share?
Yep.
Okay, I'll make you a co-host then.
Sounds good. Thanks.
Okay. Excellent. So thank you everyone for coming today. This is absolutely wonderful. Lisa, Jeffrey, and I are putting together this summer seminar. Because we're online, it seems like we're able to get a lot more people to come out. Thank you for making the time to be here. My former student, Brian Lee, is going to tell us about cops and robbers games today. So Brian, please take it away. Thank you for giving the inaugural presentation.
All right, sounds good. Thanks for the introduction, and thank you everyone for coming. So today we're gonna have a quick introduction of the cops and robbers game with many of its variants. So I'm currently entering my fourth year at University of Toronto, Mississauga, and it's nice to have the opportunity to give a talk here. So let's dive right into it. Oh, sorry. Okay. So because of the fact that this talk has no prerequisite requirements, we'll quickly go over some definition related to graphs. So in this talk, we'll only be talking about simple graph. A simple graph is defined as, actually, let me put out a chat as well so that I can see what is going on. All right, perfect.
And throughout the talk, feel free to put questions in the chat. If there's stuff that I think needs to be brought to Brian's attention, I'll bring that up. But feel free to discuss as the talk goes on in the chat.
Okay, perfect. All right. So a simple graph is defined this way as an ordered pair of vertices and edges. So for example, if we have, pen is working, okay, it's working fine. So let's say we have a graph like this with the vertices labels as A, B, and C. Then we can define this graph as a set of vertices, A, B, C, and we can describe the set of edges by the vertices connecting to it. So we have an edge between A and B, another edge between B and C, and another edge, between A and C. So this is how it's defined. Right, and we introduced the definition of connectedness. A graph is connected if there are paths between any two of its vertices. So there are no vertex that's being left out without being connected with some other vertex. And this is the kind of graph that we're going to deal with in this talk. All right, so what are cops and robbers? Cops and Robbers is a game played on graph between an opposing set of cops and usually a single robber. So the cops begin the game by moving to a set of vertices. Then the robber gets to choose a vertex to occupy. The players move from vertex to vertex along edges, usually one move per turn. Then the cops win by occupying the robber's vertex if possible, hence capturing the robber. So that's the basic definition. So here are some examples. First of all, we're going to talk about the variation where there's only one cop. So we have one cop and one robber on the graph. So this definition is a cop-win graph. So we say a graph is a cop-win graph if the cop can always win the game. Otherwise, the graph is called a robber-win graph. So let's demonstrate what that means by some examples. So here is a cycle graph. As you can see, this graph has 6 vertices. So conventionally, we call this graph a C6. This. So in this graph, let's try to play this game right now. If the cops decide to, I guess, start the game here, and as a robber, I probably don't want to start the game here because if I do that, the next move is on the cop. Then the cop can just go this way and capture the robber. So to avoid that, maybe the best decision is, let's say we can start the game here so that the cop cannot reach us in one move, right? And after now, by now, both players has already put their positions on the graph. So now the game starts. So the cop could go this way, try to get closer to the robber, and the robber will move away. And then this process will just continue and continue. Now, notice that because of the fact that this graph is a cycle graph, this game never ends because the robber can always manage to maintain a constant distance from the cop, so the cop can never capture it. So this is actually, sorry, not cop win, a robber win. So this is a kind of robber win graph. Cool. Next examples, we have a complete graph. Now things changes a bit. Let's say the cop starts here. Now, the problem for the robber is that there is no vertex that the robber can stay at, such that the cop cannot reach the robber with only one move. For example, if I stay here, then the cop can just move directly through this edge. And the fact that the reason this happens is that we have a complete graph. And by the definition of a complete graph, all the vertices are connected by some edges. So there's always like one edges that the cop can go through. So by definition, this is a cop-win graph. Okay. What about trees? Is trees cop-win or robber win? Well, we can try to play the game again. Let's say the cop starts here on this vertex, and the robber starts here. Now, if the cop moves this way, it will be not wise if the robber decides to move this way. So the robber will try to just move this way. However, it's gonna be stuck in this dead end over here. Same thing here. Regardless of what happens, the robber will probably end up in one of these vertices where the cop can occupy the middle, such that there's nowhere to go. And the same idea is going to happen here. And these vertices are a bit special because we can look at it as a dead end. If the robber end up here and the cop end up being here, then there's nowhere the robber can go. So trees are being categorized as cop1 as well. Okay, sounds good. So now we've go through some examples about psychographs, complete graphs, and trees. And it seems like it's fairly easy to determine whether the graph is cop1 or robber-win. However, we might have some examples like this. It's quite hard to determine whether it's cop1 or robber-win just by brute forcing it. So that motivated the question, what are some ways for us to determine whether the graph is cop1 or robber-win in a relatively easier or faster manner? I'm supposed to say that on the next slide. Anyway, so this is the question that we're trying to answer here. And as it turns out, here's some observations. So like we said 2 slides before regarding the trees, we can see that there are some dead ends in the graph. So at this graph below, we say that vertex 1, 2, 3 is dominated by vertex 0 when the cop is at vertex 0 and the robbers is, for example, at any of those vertex because of the fact that there's nowhere to go. And even if it looks a bit more complicated, for example, in this case, if the cop is here and the robber is, for example, on this vertex, the robber's vertex is still being dominated. And the reason is that even if I have an option to go here, to go to this vertex is still reachable by the cop in one move. Hence, it's still a dead end. And here is an important observation that we might try to argue. Removing a dead end and its adjacent edges will not change who wins the game. This might seem a bit counterintuitive. And one way we can argue this is by saying that adding a dead end to a graph does not change the winner either. Now, let's think about why that's the case. Well, given the graph, we have basically 2 scenarios. It's either cop1 or it's robber-win. Now, if it is cop1, sorry, the pen is a bit laggy. If it is cop1 and we add a dead end, now this graph is still going to be cop1. That is more intuitive than the next argument here, which is if it is robber-win, adding a dead end actually doesn't affect the chances of the robber. And the reason is that the robber can just avoid going to that dead end. So it's still going to be a robber-win graph. And by this argument, we can say that what if we have a very complicated graph? Then we slowly remove the dead end one by one, and we try to simplify the graph into something else that is easier to determine whether it's cop1 or robber-win. So here's an example. We have some dead ends in this graph. Can anyone point out where the dead end might be in this graph here? Feel free to just type it in the chat. 7, exactly. The reason is if the robber is here and the cop is occupying number 6, then that is the dead end. So what we could do is we can remove 7 and the adjacent edges. I also see 8. Yeah, 8 is also a dead end. So we could remove this one and also the adjacent edges. And then 9, exactly. Now because 8 is being removed, 9 becomes the next dead end. So we could remove 9 and the adjacent edges. Here, the same thing, we can remove 6 and the adjacent edges. now we can see that we can actually simplify this graph into a cycle graph. And we cannot simplify this further because, well, there's no more dead end, right? And by what we talked about before, in the example, we know that this C6 is a coupling, a Robert Wing graph. Therefore, the original graph here is also a Robert Wing, which kind of makes sense because the Robert can just pick any point here in the cycle graph, and the Robert can just pick not to go into the dead end and just staying on the cycle graph. One thing I should mention is that not all cycle graphs are coupling. Did I say? No, not all cycle graphs are Robert Wing. And the reason is that it is only Robert Wing if Cn for n is greater than or equal to 4. The reason is that, for example, if n equals to 3, which is going to be a triangle, in this case, this is actually, sorry about that, n is a bit laggy today. In this case, this is going to be a coupling graph, right? If the Robert move here, we can just capture it right here. So only when n is greater than or equal to 4. Okay, so that is a neat example. Now we can go back to this example right here. Now for this one, can we see what the dead end is? Seven, right? 7. Let's say if the robber is here, and the cop is at one of its adjacent vertices, for example, this one. If the cop is here, then the robber's vertex is being dominated because, well, it couldn't go this way. It couldn't go this way either because the cop can just immediately move here afterwards and capture it. Oh, something in the chat. Right. Yeah, C3 is also a complete graph by definition of a complete graph. Yes. Can a player pass their turn instead of making a move? Yes. So a player can choose not to move in a turn by the usual cops and robbers definition. Yeah. Like Brendan said, there is variations where the game is basically forcing the cops and robbers to make a move on the turn. But in this settings here, we are assuming that it is okay to just stay where they are on the turn. Yeah, thank you, great questions. All right, now back to this example. So we can remove 7 because it's dead end. We can also remove its adjacent vertices. So by that, we can remove all these because those are all dead ends. Also 8. And let's see, 4 and 5, not yet. 4 and 5 are not yet. But 10 is, right? Right, 8 and 10. Nice. And now what we get is this graph in the middle. Let me use another color to highlight it so that it doesn't look very confusing. Okay, so this is what we're getting right now. We have removed everything else. Can we remove more? Can we remove 0? Don't think we can remove 0. Because 0 is not a dead end. But what about the others? Right. Sasha had a good point. Isn't any vertex dominated by 0? Now, let's see if that's the case here. even though this graph looks like the robber has so many options, however, if the cops is occupying 0, then the robber has a problem because let's say the robber is staying here. Now the robber has 3 options, technically 4 options. The robber can stay where they are, then the cops can just move forward and capture it. The robber can move to 4. That's no good because the cop can capture it this way as well. The robber moved to 6, similar idea. Or the robber can just move to 0 and just, I guess, surrender. So as you can see, no matter what the robber does, it will be captured by the cops. So in this case, we actually find out that all the other vertices are categorized as a dead end. And we also remove all the adjacent edges. So what are we left with if this happens? We're left with one single vertex 0 with no edges around it. Now, what does this tell me? Technically, this is still a graph. It's a graph with one single vertex and no edges. So if I want to play the game on this graph, the only option I have is if cops and robbers starts on the same vertex. And this is automatically a coupling graph because they only have one vertex to go. So we managed to simplify this entire extremely complicated graph into one single vertex and say that it is coupling. So this is one approach to see, to take in one complicated graph as an input and output whether it's coupling or robber win. Okay, and here is some theorems to justify what we just done in a more rigorous setting. And it is done by defining something called a closed neighborhood. And before that, we have to introduce an open neighborhood. So an open neighborhood of a vertex is the subgraph of G induced by all vertices adjacent to V. So what that means is that, for example, if we have a vertex here denoted by A, then B and C are its neighbors. D is not. So we're only talking about adjacent vertices. So that's open neighborhood. The open neighborhood of A here, denoted by neighborhood of A, is the set with B and C in it. Now, closed neighborhood is slightly different because closed neighborhood includes the vertex itself. So in this case, the closed neighborhood will be A, B, and C. Now, here is a theorem that tells you how to determine if a graph is coupling. So a finite graph is coupling if and only if there is a linear ordering of the vertices from V0 through Vn, such that for each I less than n, there is a j that is greater than I and less than or equal to n, so a j in between I and n, such that the neighborhood of Vi, the closed neighborhood of Vi, is a subset of the closed neighborhood of Vj. In other words, Vi is dominated by Vj. And this is basically equivalent to what we have done in the previous 2 slides, trying to eliminate dead ends. Okay. Right. Gonna take a pause here, and then we'll move on. All right. Is there any questions so far? I think it's a good time to take a pause and talk about some. Okay. If not, let's talk about cops and robbers, but this time with many cops. So in order to talk about many cops here, we have to first define a concept called cop number. So a cop number of a graph G, usually denoted as C of G, is the minimum number of cops needed to win in G. Of course, win here, assume that it's winning for the cops. So in this case, all cop-win graph that we mentioned before has cop number 1 because you only need one cop to win the graph. Oh, let me see the chat. Yeah, exactly. So dominated means that its closed neighborhood is a subset of the dominating node's neighborhood. Yeah, that's exactly the definition. Yeah, thank you. All right, and what about cyclograph with more than 3 vertices? Now, we talked about this before that those are robber win graph, but now we introduce the idea of cop numbers. So we're basically asking how many cops do we need to win the game on a cyclograph with more than 3 vertices. For example, C5, let's say. 2, exactly. That is correct. And the reason it's 2 is because, let's say we have cop 1 over here and cop 2, and then the robber is here. Now, before, the robbers was able to go around the graph and try to avoid cop 1. But now, cop 2 can just simply try to close out this, this cycle for the robber. So it will be very easy for the 2 cops to just trap the robber in the middle. So cycle graph with more than 3 vertices. So cop number of cycle graph Cn is equal to 2 if n is greater than 3. Okay, cool. All right, here is another idea related to like how complicated is the process of computing cop number for a graph. And it turns out it is exponential time complete. So an equivalent setting would be trying to play chess on an arbitrarily large but finite board. And this is a result published by William Knisley and Anthony Bonanno. So it's not an easy task per se. Okay, so how do we determine the cop number of a certain graph? Oh, that was William's result only? Oh, sorry about that.
It's okay. He was a postdoc with me at the time, and it was a huge result. And I did read an early draft of the paper, but yeah, I was not a co-author. It's just Bill, just William.
I see. Yeah, thank you for clarifying. Thank you. Yeah, it does relate to the complexity. There is actually a huge conjecture in cops and robber related to complexity. I think it's a couple slides down. I think it's one of the deepest problems in this field. So, all right. So here's a theorem here developed in 1983, which is basically saying that every planar graph has cop number M-most 3. So a quick definition of planar graphs. So planar graph is basically a graph that can be laid out without any edges intersecting each other. So for example, let's say the complete graph K4. This is not a planar graph because there is no way that you can draw this graph without this intersection here. Assuming that we're drawing this on 2D surface. However, if you have a graph that looks like this without any intersections of edges, then yes, it is a planar graph, similar to this. So the theorem is saying that every planar graph has cop number at most 3. So you don't need more than 3 cops to win the game. And here's another definition that we're going to need to, I guess, like move further in this talk. So it's called girth. And the girth of a graph is the length of the shortest cycle contained in the graph. Now, let's do an example of this. So here's the Peterson graph. And the Peterson graph has girth 5. Now, what does that mean? That means that, for example, if I start from this vertex over here, and I try to go back to this vertex. The shortest path I can take needs 5 edges. So for example, I can go here, 1, 2, 3, 4, 5. It's 5 edges. Or I can just go around this stars in the middle. 1, 2, 3, 4, 5. That's still 5 edges. And there's no shorter path than that. So we say that the Peterson graph has girth 5. Now, this turns out to be a very useful concept in this case, because of this theorem here. Let G be a graph with girth greater than or equal to 5, like the Peterson graph we just saw. Its Cobb number is greater than or equal to the minimum degree of G. So this is an interesting result because it does have an intuitive sense to it. Because intuitive speaking, if every vertex of G has at least D adjacent edges, so that also describes its degree, right? The degree is equal to the number of adjacent edges. So if every vertex of G has at least D adjacent edges, but there are only D minus 1 Cobbs, then the robber can sneak away or escape through the unguarded edges. And we need a restriction that the girth is greater than or equal to 5 to eliminate the possibility of an individual Cobb being able to guard multiple edges at the same time. And by guarding here, we mean that the Cobb is able to move to multiple edges at the same time for the capturing. So this is an interesting theorem. All right, now some open problems in Cobbs and robbers. Before someone mentioned runtime in the chat, and this is something very interesting. So it's called the Maynard's conjecture. And it essentially states that for a connected graph G, the Cobb number is equal to O of square root of n. So what does that mean? For those with a computer science background, we know that this basically means that as the number of vertices n grows, the Cobb number grows in a square root of n kind of rate. And I also attach a translation of this problem. We can also say that this problem is equivalent to saying that the largest possible Cobb number of an n vertex graph is square root of n. So statement 1 and statement 2 are basically the same conjecture. And this is considered one of the deepest problems on the Cobb and Roberts game. And many more open problems appears when we look at like many variations of the game, which we are going to talk about now. All right, so let's talk about some variations. So the first variation is what we call lazy Cobbs and robbers, which basically says that despite the fact that we have multiple Cobbs, we're only going to let one Cobb move during each round. And notice that this is only different from the regular Cobbs and robbers if we have multiple Cobbs to begin with. So here's one variations. For some of these variations, I'll also attach some like theorems that I find interesting that we can talk about. For example, the next one here, I think this is a quite recent one. It's more looking at this problem in a probability kind of like perspective. It's called Tipsy Cobbs and robbers. And basically, we define two types of moves: a tipsy move, which is a random move, and a non-tipsy move, which is the optimum move for the Cobbs or the robbers. So a random movement flavored as tipsiness is included for both players. So this limits their ability to execute the winning strategy. So in this iteration, both players move simultaneously in rounds and are not aware of the move the other players will make. And what that means is that, for example, if we have a graph here, let me draw something. So for example, let's say in this graph, I have a cop here and a robber here. Oh, that's a bad example actually. Let's say there's another vertex here. So in this case, if the robber is not tipsy, the right move would be to move this way to like get farther away from the cop, or to just stay there if it wants. But because of the fact that the robber might be tipsy, in a probability sense, the robber might make a random move to just go closer to the cop. And the same thing for the cop. Let's say there's a 50% chance that the cop is tipsy. Then if the cop is tipsy, the cop will just make a random move. So it could stay here, it could move this way, or it could move this way. However, if it's the other 50%, if the cop is not tipsy, then the cop will definitely move this way and just capture the robber. So there is a lot of stochastic and probability going on in this scenario. And one very cool real-world application is that we can actually use this to model how a white blood cell track down and eliminates bacteria in an organism. And there's a citation here that for those interested, we can look at. So yeah, very cool applications. And we have zombies and survivors. So slightly different. The zombies here, being of limited intelligence, has a very simple objective in each round, to move closer to a survivor. Now, notice that being able to move closer to the survivor might not be the optimal strategy sometimes. So in this case, the zombie must move along some shortest path on the graph. And we have some lemmas going on here. And we can actually justify most of them without, I guess, diving into very rigorous proof. So the first one here is that in any graph G, the cop number is less than equal to the zombie number, where Z of G denotes the zombie number. So the number of zombie needed to win this game 100%. And this kind of makes sense because in the cop and robbers game, we assume that the cops are executing the optimal strategy. Where in the zombie game, we're saying that the zombie just pick the shortest path. But the shortest path sometimes does not mean the best strategy, because sometimes they might move to a shortest path, but it's not a dominating vertex, for example. Then the robber might be able to move away from this. Another thing is that on a tree, it really doesn't matter. The zombie number and the cop number are the same, just one. Because on the trees, while moving closer is essentially the optimal strategy in this case. And same thing for cycle graph. For cycle graph with n greater than or equal to 4, we see that the zombie number and the cop number are both going to be equal to 2. And here's a theorem here. If a graph is zombie win, then it is also cop win. Well, if zombie can move closer and closer and try to capture it, then the cop can execute the same strategy, which is going to be the optimal strategy in this case. However, if a graph is cop win, then it is not necessarily zombie win. I actually don't have a counter example. I actually don't have an example for this. So if anyone could come up with an example of this, that would be super cool. But I think it makes sense because sometimes moving closer does not mean moving according to the optimal strategy. Yeah. Oh, I see the chat. Can you explain why? Yeah, of course. So let's say we have a cycle graph Cn. Let's assume there's many other vertices here, but it's going to be a cycle graph. So why is the zombie number equals to 2? Well, let's say we have zombie 1 here and zombie 2 here, right? Sorry, that looks a bit messy. Let me clean it up. Okay. Now, let's say if the robber is here, and as you can see, the strategy for zombie and for the cops are basically the same, because we don't really have much options here. For the cops, the optimal strategy will be to move closer to the robber. And for the zombie, moving closer is the optimal strategy. So in this case, the two problems are essentially equivalent to each other, right? Because by definition, like moving this way is going to be moving closer to the robber. Like the zombie wouldn't want to move the other way. And the same thing for zombie 2 here. Moving this way might be closer. So therefore surrounding the robber regardless. Yeah. So the reason why a cop win grab is not necessarily a zombie win grab is because there's some. Oh, no, sorry, I should explain. So all the variations here are independent of each other. So tipsiness are the previous variation, but the zombies one are completely different. So in this case, there is no probability and there is no tipsiness. Yeah. I actually think there is an example, but I have to go all the way back. Remember the example where this happens? Let me move this to the side a bit. So this example right here, hopefully I'm memorizing this correctly, but I think this is a good example that might work. So this graph right here, this vertex here in the middle is the dominating vertex of all the other vertex, right? So if this is a robber, this is a cop playing the game, the optimal strategy for the cop would be to just move to the middle, and then the game will be over. However, if this is a zombie playing the game, and let's say the zombie starts here, and let's say the robber starts here. Actually, in this case, survivor. It doesn't make sense if zombie is chasing the robber. I mean, it could be the case, but we call it survivor here. So let's say survivor's here. Now, the problem is that the zombie might not move to 0 in the middle. And the reason is that this path has length 2, and this path has length 2. So it could go either way, right? And if the zombie chooses to go this way, then the problem is that this graph is similar to just a cycle graph, C6. And in this case, this is going to be a survivor win game, right? So the zombie might not recognize that there is an optimal strategy in the middle. So that's why if a graph is cop win, that doesn't necessarily mean that it's going to be a zombie win. Okay. I think I have one more variation. Right, so just some more variants that I want to talk about. So infinitely fast robber, this was actually introduced yesterday during Canada. I was there. It's introduced by William. So basically the robber can traverse an arbitrarily long cop-free path in each round. So the robber doesn't really have a speed limit. It could move to any vertex it wants to, as long as the path is not being blocked by any cop. So that's one very cool variation. Another one is called hyperaric cops and robbers. So this game involves imperfect information for the cops, such that they cannot see the robber if the robber is within the end neighborhood. So this is directly quoted from Anthony's research. Essentially, the motivation for this comes from adversary networks, where edges denote competitions or rivalries between vertices. So, for example, say in this case, let's say if the cop is here and the robber is at its neighborhood, maybe not that close, maybe let's say the robber is here. But let's say the cop cannot see robber within length 2 within its neighborhood, then the cop might not know that this is the optimal strategy. So there is an area of blindness for the cop where the cop does not have any information of what's going on. But outside that, the cops have perfect informations. So that's an interesting variation of it. think that's everything that I have to talk about. The rest is the citations that I used in this talk. Again, I started preparing this talk this week, and I mostly just started reading a lot of research on the web. And also yesterday it was very lucky for me to attend, I think, like 3 talks on cops and robbers during Canada. So yeah, thanks everyone for joining. I think we can use the rest of the time for free discussion and everything.
Yeah, thank you very much. Thank you, Brian, for giving a wonderful talk and starting off this talk series. That's absolutely awesome. If people have questions, please throw them in the chats. We'd be happy to spend the next couple minutes talking. There's also, I just want to say, this seems to be a hot topic. We've got a talk coming up tomorrow at Talk Math with Your Friends about this exact same topic, but focusing on lazy variants. So that is going to be Brendan Sullivan from Emmanuel College at Talk Math with Your Friends, and the info for that is in the chat. So thank you very much for coming, folks.
There are some interesting questions in the chat, such as are there variants on infinite graphs? Again, I'm not sure, but I don't think it's meaningful if it's on infinite graph, is it? Because then there wouldn't be capturing because of the fact that the graph is infinite.
Hi there, Xingyu. It was a really great talk. Very much enjoyed it. And I'm impressed that you did this in a week. That's very good. The answer is yes. I mean, you can look at any of these parameters on infinite graphs. Of course, the difficulty increases exponentially, and some questions are less meaningful, but you can define the COP number here. The COP number becomes a cardinal, infinite cardinal. And many techniques don't sort of apply. So for example, what you described with regards to the Novikowski-Winkler Keogh characterization of Cockburn graphs, the dismantlability, there's no direct analog of that for infinite graphs. There is a characterization that Novikowski-Winkler gave in terms of relations, like these certain binary relations, this tower defined in terms of ordinals, but it's more complicated and less transparent. So the short answer is yes, but it's complicated.
I see. Very interesting.
Thanks for the talk, Greg. Very good. Very interesting.
I have some variants I might suggest. I would suggest maybe you could have a variant where the cops are a team controlled by different actual people, and they don't necessarily have complete information as to what their teammates are doing. And so there are various variations on this theme depending on how complete their information is. Like what now you have is effectively complete information. One person is controlling the entire team, but you could have, independent people who have some partial knowledge or no knowledge of what their teammates are going to be doing.
Yeah, that sounds very interesting. I also see a comments in the chat, prisoners dilemma meets cops and robbers, maybe.
Does anybody know the proof that the COP number of a planar graph is 3?
Yes, let me get you the link.
Yeah, sort of the thing that comes to mind for me is that maybe the cops always want to occupy like a particular color, like they always want to stay on blue or something, or maybe they want to stay like to always keep the robber on maybe a pair of colors or something.
So I've actually read this proof. I don't remember it relating much to the four-color theorem, but from what I remember, there's a way to prove that two cops can kind of occupy a big cycle in the graph, and then because it's planar, that divides the graph into the interior inside that cycle, and then the exterior, and the robber must be in one of those two places. And you can prove that the cops can maintain the control of that cycle, so the robber cannot pass from inside to outside, or vice versa. So they've kind of constrained the robber into a certain section. And then you can use the third cop to then come inside and capture by kind of narrowing that cycle. That's my remembrance of the proof.
Oh, that's really nice.
So Parker, is this a weekly seminar? So do you have any plans for next week?
Yes, thank you for asking. You're making the job of hosting this very easy. So thank you very much for coming. We are looking for speakers. Lisa and I are looking for more speakers. This is a seminar intended for undergraduates. Luckily, adults are also welcome. Thank you for coming out, all the profs and emerituses. This is awesome. So if you'd like to propose a talk, if you have a talk in your back pocket that's suitable for undergraduates, please contact the organizers. Next week, I will be talking about the probabilistic method. So giving an introduction that talks about Erdős's examples of interesting chromatic number calculations, this sort of thing. And this will be accessible to everyone, no background required. So that's next week. You can find the information either on our website or on research seminars. So if you go to either of those links, the Zoom information